All right. In the next 25 minutes or so, we are going to sharing some work we have done at Intel and for developing the DPC++, C++, Fortran OpenMP compilers for the Intel's CPU and the Xe GPU. And I will cover the language programming model and the compilation flow and the runtime architecture part. Then Andrey is going to talk about some examples and the MiniWeather code to show how exactly the OpenMP can be used to run it on the GPU. All right. So the agenda for today's talk, we are going to have a very quick recap of the GPU overview and take a look at the software stack, the big picture of the software stack we are building to enable the CPU and the GPU on this heterogeneous environment. We quickly go over the DPC++, C++, Fortran OpenMP for Xe accelerator programming model to give you a high-level view what we are doing, what kind of features we are covering. Then quickly go over the compilation flow and the runtime architecture, followed by the usage examples. Okay. All right. So at the Hot Chips 2020, the Intel chief architect of the GPU, David Blazer, he did give the nice talk on the Xe multi-tile GPU has been designed by Intel. And we are going with a 1 tile, 2 tile, and 4 tile. So basically, if you look at the scaling from FP32 point of view, it's going to have a pretty good scaling. So, and on the whole of this architecture, essentially, we're going to add a whole bunch of the sub-slides called the exclusion and with the exclusion unit array. And this is going to become with hundreds of the exclusion unit. And each exclusion unit going to have the 8 threads. Okay, those can. So this is essentially, we are not going to dive into any details today. If you are interested, go to the Hot Chips presentation. But the key message we want to deliver today, under this architecture, there are going to be thousands of the threads we have to utilize for, fully utilize the machine. Okay, that's the sort of the key message. Then with that kind of hardware, what kind of the hardware, given that kind of hardware, what kind of the software stack we are building at Intel, try to enable those kind of new emerging hardware. So basically, if we look at the HPC and the AI application, there's a whole bunch of existing applications around the world already implemented with the OpenMP, and of course, a lot of scientific code is implemented with Fortran. And also the national labs and the DOE labs, they have been building this COCO's Rajas framework and C++ based on the modern C++ that people can actually leverage without going directly using this programming language. They can actually use high-level frameworks to write the application. But on the whole, those framework application and the framework can directly use language we are developing like data parallel C++, OpenMP C++, Fortran, and other script language. Of course, besides those language support, Intel is going to provide a whole set of the API-based program model like MKL library, TPB library, OpenRhino for AI, and the MPI for sure. For HPC application, MPI is the most important one. We are also going to support the parallel STL, which is one of the modern standardized the template library for C++ from the C++ standard. Beyond those things, we also have a whole set of the porting tools to convert, for example, from other kernel program language model to use a data parallel C++. We call the migration tools. And also we have a whole set of the analysis tools to the VTO analyzer, advisor tools, inspector, and roofline analysis tools, those kind of things to help the user to improve their productivity to fully transition from the the sequential C++ or Fortran code or other program language to using the OpenMP or data parallel C++. Both Intel's data parallel C++ is built on top of the corners of the SQL language standard. And the OpenMP, of course, we are fully aligned with the OpenMP standard as well. So of course, after this one, we have a whole set of the low-level GPU software stack called GPU driver and OpenCL runtime. And also after that, you can map to those to the our CPU, GPU, and the AI FPGA sort of hardware, right? That sort of give you the high-level big picture of the frameworks and the AI application, taking the advantage of the Intel's software stack to map to the hardware. Okay. So let's take a quick look at what is the DPC++. As I mentioned, the DPC++ is built on top of the SQL, which is Corner's standard. They're going to publish the SQL 2020 before the end of this year. So, and also in the DPC++ language, you have a whole set of the features like how to do the buffer, essentially how to do the memory management and the data movement. And also Intel proposed the unified shared memory support. So user can write a pointer-based program, then the memory you allocated, you can actually accessible by the both host and the accelerator or GPU, right? Of course, we have a scheduler. We can support multiple type of the parallelism, and also given this heterogeneous environment, you have to have a set of the device management, right? Then also we try to improve the interoperability support with OpenCL. For example, DPC++ can interoperate with the OpenMP as well. Of course, there are some error handling stuff, right? And beyond that, there's a whole bunch of the building, rich set of the building functions. You can use the mass functions and the parallelism management functions. Also, the data types, the scalar data type, vector data types. And of course, the SQL and the DPC++ allows the target a specific extension for the user to get the maximum performance. So those are sort of the top 9 or 10 components which compose the DPC++ language. Okay. And the basic execution model of the DPC++ is essentially based on this ND range model from the OpenCL, and also is very similar to the CUDA's threading model as well. So basically, that we can support up to 3D partitioning among the of your work group. Each work group you can have a 3D dimension, right? So you have a global work size. When you partition there's a global work group to the local work group, then or you can just call it work group. So basically, based on the size, you can see there's a multiple work group is created. Then each work group, you can map to them to threads, or even inside the work group, you can have a subgroup. You can map to the SMD hardware. So there's a lot of magic happening from the high-level program model actually down to the mapping to the hardware. So we are not going to dive into the details today, but this is basically aligned OpenCL execution model. As long as you're familiar with OpenCL and the CUDA execution model, the DPC++ program model is easy to be understood. Okay. So that's covered the DPC++ part. For OpenMP part, since we started from 4.0, OpenMP standard has added a whole bunch of the extensions to support the accelerator core processors. And the OpenMP program models was evolved from the original shared symmetric program model to the heterogeneous program model by the application domain of the OpenMP also span over multiple application domain beyond just the traditional scientific computation. It has been used in the signal processing, medical image processing, autonomous driving, and even some kind of teaching appliances, sort of the simulation kind of thing. Okay, so the application of the OpenMP has been spanned quite a bit over the past 5 to 6 years. Okay. And let's focus on the offloading program model. Essentially, it's very similar to any other language. It's just a different level of the presentation. OpenMP is pragma-based, right? So user don't have to write explicit kernel function. So basically, in the OpenMP, you can use a target construct to mark your code to be offloaded to the device or accelerator. Then there's a map clause, essentially, and you can use that to perform the data transfer. And also OpenMP beyond those offloading, OpenMP supports both synchronized offloading and asynchronized offloading. And basically, each OpenMP target construct is implicitly treated as a task. You can run it by the separate thread. Then you can do the both host thread and this thread, target thread can run in parallel. And the target thread actually can perform the offloading, get the data back, and with the host thread can continue to move on to running, and the code needs to be running on the CPU. That's the way we are working to support the asynchronized execution. As I mentioned, basically map class allows us to create the data environment on the device. And in the OpenMP 5.0, that's a new feature added to OpenMP 5.0 called unified shared memory. When you use this pragma to require the compiler to generate the code to support a unified shared memory, for example, OpenMP target allocate function, essentially the memory allocation going to happen in the allocated memory from the USM memory. So in that sense, that pointer returned back, you can use the use on both host and the device. That's basically the extension starting from 5.0. Okay. So this is a set of the the subset of the OpenMP construct that we were able to support for the device. This is not unique for Intel. Basically, IBM, NVIDIA, AMD also they're pretty much doing the same set of the support for their GPU or accelerator, because not everything inside the OpenMP which can be running on the host can be supported on the device. Because, for example, the tasking model, the existing GPU, there's no efficient support for the dynamic scheduling on the GPU because there's no OS running on the accelerator, right? So this is pretty much all the wonders is targeting the same set of the constructor for the accelerator. And also we look at all the standard industry standard benchmarks like a spec SEC, and we look at a whole bunch of the HPC applications our customer has been using. We know what is exactly important for them to support in our compiler to enable them running their application on the Intel's hardware. Okay. Of course, beyond the language construct, there's a whole set of the runtime functions need to be run. Some functions is only run the host, and a set of the functions are going to be run the device. You can get the information you need for you to control your parallelism and tune the performance. So we don't need to go through one by one, given the time we have. But this will give you the high-level overview of all the features we are going to support on the Intel's CPU and the GPU. Okay, XeGPU. So now let's probably, since I'm the compiler engineer, so I'm just want to go through quickly and to see how this just-in-time compilation works for when you try to compile your code running on the accelerator going through this jet called just-in-time compilation, right? So basically you have your .cpp code, which is either C++ or OpenMP or Fortran code with OpenMP offloading inside. You go through our front end, you go through LVM IR optimization, because all our next generation or current generation of the Intel's C++ and the Fortran compiler is going to be built on top of the LVM infrastructure, which is a modern compiler infrastructure for the most of vendors have been using. Okay. Then we generate the object file, or we generate a .bc file, and then the .bc file, we link them together. Then the BC file can be linked to the sphere, which is a portable IR target for the multiple, can be used for multiple device, for the device combination path. Then basically, eventually, the host path is the same as what we did before. We generated the .lbj file, then we go through the host linker, generate what we call a fat binary or fat executable. And this fat executable, and you see on the device combination path, is not really the final target specific binary, right? It's called a sphere read. Now at the jet time, we invoke the target specific compiler, actually translate the sphere read to the target binary. That's what we call the just-in-time combination. The advantage of the just-in-time combination is the binary, the fat binary ship you can use for multiple platforms, right? And also just-in-time compiler, since at the runtime there's more parameters it's knowing as a constant, so we can do more optimization. So this is a just-in-time combination. Then, of course, some people want to use like our FPGA team, they want to use a ahead of time combination, which is called a static combination. So the difference is we don't generate the spare V after the LVMIR linker. The rest is pretty much the same as just in-time combination. We just convert, instead of generate spare V, we directly invoke the target specific compiler to generate the binary, target specific binary. Then, of course, we need to wrapper this one as to create the right format. Then we can use the host linker to generate the what we call the fat object, fat Excel binary. So those fat binary can be running on the host and also offloaded to the GPU. So this gives you the really high level overview of our combination flow. Around this architecture level of the design of this combination flow, we have a whole bunch of the tuning inside to make sure we generate, deliver optimal performance for our users. Okay. So the next slide, we are going to talk about the high-level runtime architecture. So since the Intel's Xeon 5 project, Intel has proposed this libopenp target ABI. This ABI has been well adopted by the community, basically, as of today. For example, AMD and IBM, they are also targeting this libopenp target. On the whole, they are building the target specific what they call the plugin and runtime. So for Intel, we are building the OpenCL plugin, and also we are building this level 0, which is Intel's new low-level runtime, which is supposed to give us the high performance for Intel's Xe GPU. So basically, we are building both OpenCL plugin and the level 0 plugin, and those plugin is based on this level 0 low-level runtime, all based on OpenCL runtime. And on the host side, the CPU OpenCL runtime is built on top of the TBB. And then the TBB, TBB also is well adopted by the community. It's running on the Intel's CPU, right? So basically, on the OpenMP host side, there's nothing changed. So basically, we are using OpenMP runtime running on the CPU, and OpenMP device runtime, we're going through OpenCL stack and use the TBB running on the CPU. On the GPU, basically, we're going through the OpenCL and the level 0 plugin and the OpenCL RT, and they goes to the KMD driver and eventually map to the the GPU. The current the one on the market is called Gen 9. And the future, the new one come out going to come out in the future is called the Xe GPU. So with that, you can see we can truly leverage the ABI we defined with the community, and all the software stack can sharing a lot of low-level software stack for the DPC Plus and OpenMP offloading as well. So hopefully this gives you the high-level vision of what we are building to enable your application can be run on the Intel's GPU and the CPU. Okay. So next few slides, we're going through some examples. Andrey from Intel's application engineering team is going to walk through a few examples to give some intuition for you. Okay, go ahead, Andrey. Andrey, can you hear me?
Thanks, Xinmin. Yeah, can you hear me? Just to check.
Yes, you're good.
Yeah, perfect. Yeah. Thanks, Xinmin, for introduction to one API. It's for Multicore workshop. So it's the first time. So on this year we are talking about one API and common Xe architectures. So as well as also as our Xeon CPUs and other architectures, which is important in our current and future heterogeneous computing time. So yeah, just an example of Fortran OpenMP offload codes of so weather and climate ESM segment. So it's heavily legacy Fortran applications, and so developers are thinking about using accelerators on next generation supercomputers. They may consider as a natural transition is to use OpenMP. DPC Plus, it's a great model for C++ application. It will naturally fit, and for Fortran legacy applications, yeah, OpenMP could be better choice. And so this example just illustrates simple code with key OpenMP 4.5 and 5.0 clauses for offload. So on this sketch on the left, we see simple, simple kind of stream type of workload. So it's basically just one loop, and we see here the key OMP target distribute. So this is a launch team of threads which are executing on accelerator. So I'll give an example which is more relevant to weather just in a minute. Just if you can move to next slide. Yeah. So this is basically so this slide here. So it's just a simple, very naive example of computing of pi number and comparison between OpenMP offload current in C versus DPC Plus version of the same code. Just if you go to next example, which is more relevant to weather, on next slide, I'll talk more a little bit. Yeah, so this is so we took a MiniWeather application, which is a mini app developed by Dr. Matthew Norman from Oak Ridge. And it's a relatively simple code, and it has a great diversity of different implementations, starting from our flat MPI code, which is still very common in weather and climate community, and other implementations like OpenMP, hybrid MPI plus OpenMP, and OpenMP offload. And also versions for accelerators based on OpenACC and some C++ with backend in CUDA and HIP. So this is a great example of weather workload, which is to evaluation of different programming models and capabilities of different implementations. For example, OpenMP. So basically what it does, it solves, it represents similar algorithms what many weather codes like unified model, WRF from climate CSM, what is happening in dynamical course, which is stencil computations. And an example of MiniWeather, just like there are just a few maybe just one stencil to compute fluxes with finite volume schemes, and Runge-Kuta time integration, which is also very common in many community and production weather codes. So on the right, we see just a key OpenMP 4.5 clauses which are necessary to offload code to accelerator. So in this case, it's I took as an example a code written in C. So there is similar version in Fortran. So here we see like three types of one of the key probably OpenMP 4.5 clause. It's map. So we map data between host and device data environment. And there are like three examples in this mini weather application. So it's two allocation, alloc and two from. This is basically gives a different rule to copy data from to device or vice versa. So mapping the data from between host and device. So and it's basically two gives a rule that the data should be copied to enter. So to from, it's both to enter and to exit from accelerator, and allocation, so it's just no copy. And this is necessary to keep in mind when programming for GPUs or other accelerators with data movement. It's a critical for performance. And next loop is just update of during one Runge-Kuta stage, update of state variables, and here we use key OMP target team distribute, and also parallel for SIMD, and collapse with triple nested loop to have enough work for accelerator. And this is a very common example, and will be used probably in many applications which are targeting for OpenMP offload. So this probably essential part, these two mapping and team distribute clauses. So in next slide, I'd like to show an example of compilation of MiniWeather code and running it on Intel DevCloud, which is currently available for developers, and I encourage you to try it. So on left-hand side, we see an example how to build what modifications are required in CMake file to compile it with one API compilers. So this application basically, so we need to source one API environment and use special wrappers for one API compiler. This is ICX for C, ICPX for C++, and for Fortran it's IFX in contrast to classical Intron compiler, which is iFort, ICPC, and ICC. And also, yeah, to be able to offload, to generate offload target code, so you need to use -fi OpenMP and fi OpenMP targets equal SPRv64. Xinmin previously mentioned what is this compiling flow, and so this SPRv basically says what should be compiled on a device. So SPRv, it stands for standard portability. I think standard portable and intermediate representation on GPUs, and it's a open standard, and it's maintained by Kronos Group. So and DPC Plus and one API in general. So it's just Intel implementation of this, and yeah, and also, yeah, to run this workload, so you'll need to use the environment variable for offload, which is the OMP target offload equal mandatory, and then just launch your application OpenMP. In this case, it will be just MPI plus OpenMP offload. And in the right hand side, we see an example of running it on Gen 9 Intel graphics, which is attached to Intel i7 core processor. So it's a 4 cores, just a simple desktop processor with 2 graphics cards. And we see this application successfully running on Gen 9. And yeah, at the end, so we check correctness of the results. That the results was actually accurate, and also, yeah, some visualization of flows shows no visible difference between CPU and GPU obtained result. So next slide. Yeah, so I'd like to call attention of developers to keep in mind that there is no free lunch, and when we are working on development of models for GPU, we need to keep in mind available parallelism in a workflow or workload, and how to map this parallelism to device or to hardware capabilities. So if basically there is no enough work for instance, if there is a short loops, or there are a lot of conditionals, and this is gonna make performance very bad, and there is no point to offload some parts of the workflow. But at the same time, so some parts of the weather algorithm workflow might naturally fit to GPU, and we know some successful example, for example, for AVX 512 optimization, and it's SIMD logic. It's similar logic will help on GPU offload. When we have, for example, a code which has enough compute, for example, radiation, and with proper data structures to avoid conditionals inside loop body. So then, yeah, this could be a great example. And yeah, and also, yeah, try to avoid moving data from host to device, which is yeah, like I mentioned in previous slide, map clause. It's important to use it with right policy, which data should be left on GPUs and which should be exchanged between GPUs and CPU. Yeah, so and on next slide, yeah, this is actually the last slide. So we'd like to call attention of developers and try Intel DevCloud. We've already pre-installed one API. Currently, it's beta. So later this year, gold release will be available. And DevCloud currently comes with multiple Xeons GPUs like Gen 9 and DG1, which is good for single precision for if you have workload with single precision. So DG1 also can be used for development and analysis of offloading of weather and climate application. And also, yeah, a few important links to one API, open source code and compilers, and also one API specification and documentation from community. You'd like to call your attention, and please feel free to contribute to development of standards and try also our hardware and compilers compatibility tools if you're working on targeting DPC Plus and have currently C++ or CUDA code. So you might try also CUDA compatibility tool, which is part of one API. Yeah, so I think I can stop. I can stop here and leave some time for questions. So I saw in chat was a few questions, so we may respond now.
Yeah, there's a number of very good questions. I saw that. So let me answer the first one. Can everyone still hear me? I guess so, right? The first one, basically, we have been working with the code play. The DPC Plus actually can work on the NVIDIA GPU. So this is one of the open source project has been done with the community. So the answer is yes. Okay. And also the DPC Plus version of the MiniWeather. Andrew, you want to take that question?
Yeah, sure. Yes, so we haven't yet contributed yet to GitHub. So we will definitely do this. Yeah. So okay. Yeah.
So the next question is SQL seems to hiding the GPU pointer to the buffer object. Yeah, and actually in the SQL 2020, Intel has proposed this USM pointer. Actually, there are 3 API provide for you to get the GPU pointer. It's really the GPU pointer. You can use, for example, malloc_device, you get a GPU pointer, or you can use a malloc_shared, you get a USM pointer, or you can use malloc_host to get the host pointer. Host and shared, both the host memory and the USM memory can be accessed by the device code from the GPU directly as well. But only the device pointer you allocated can only accessible by the code on the device, which is the host code cannot access the memory or the device memory. Okay, so we provide a pretty rich set of the API for you to do this direct GPU pointer access. Okay. The next question, do you provide the tools to convert the CUDA? That's a good question. Actually, that's what I mentioned, called the Intel, we call the migration tools or Intel's compatibility tools. So you can convert the CUDA code to the DPC++. There's actually quite a bit of application converted successfully, of course, with assistance from the application owners too, because there's a lot, this is not a translator. That's why we call the migration tools. Pretty successful. And multi-GPU program model enable the MPI. Yes, we are enable the multi-GPU under the MPI. Actually, for the remember for the Xe GPU, we are going to support 1 tile, 2 tile, and 4 tiles, right? So basically, every tile you can actually have map one MPI process to the single tile. You don't have to use the entire GPU. You can just use 1 tile on the GPU, or you can use 2 tiles on the GPU. So we have pretty rich program model for you to perform those kind of level of the control from both at the language and also from the API point of view. Okay. Hopefully, is there any other questions? I believe I answered all the questions.
All right, thank you. Let's move on to our final speaker, Suret.
Thank you.
Yeah, thank you.
Thanks.